So, hi, I'm Paul, postdoc at Chartered University, supervised by Dave Campbell and Bruce John at SFU. And I will just present an ongoing work about the characterization of southern resident clearway coils using a particular filter for frequency reach perspective. So just to words about the southern resident clearway local repertoire, but we already had some few words with our presentation. So southern resident clearway has a specific distinct vocal dialect compared to other clearway. But they share the same call repertoire between the call three pods, and some few call types are preferred by one or another pod. So the challenge in this work was to help annotator in order to identify call types, because annotation is a challenging task because you have to orally and visually inspect long audio files. They can be also hard to identify due to the complexity of the sounds or also similar sounds such as unbacked. Calls can be incomplete and this can be noisy environment. And the human perception plays a key role in annotation. So one expert would have different labels from another one. So the goal of this work was to decompose variability in frequency ridges of specific southern resident clearway coils to get a better understanding of the distribution of behaviors within this call type. So we are trying to model the variability inside each call type. So it could help us synthesizing new calls. So as presented by Oliver, it will be a kind of generative adversarial networks. But it's from a biological point of view, it could also help to look for structural differences between pods of southern resident clearway. This is one tool to achieve this goal, but there are other tools such as deep learning, and Val will also introduce you with autoencoders. So the workflow of this work is pretty simple. The first step is to extract frequency ridges in a time window of a spectrogram. And then we perform what we call the functional principal component analysis, or FPCA, to decompose the variability. The dataset is simple because we just wanted to have like kind of proof of concept. So we just selected in the Ford catalog published in some years back 7 call types, so which are preferred by one or 2 pods, such as S1, S4, S16, S17, S19, S66, and S34. And we try to extract the ridges. So we did a benchmark of ridge detectors using different softwares, but also different available codes on the web. But we were unhappy because, as you can see in the different for example, we have like a lot of small parts of ridges that are not linked, and this could bias our decomposition of the variability. So we decided to create our own ridge extractor in order to meet the requirements for the functional principal component analysis. So this slide is just about data massaging. So first we just take the raw spectrogram, we denoise it, and then we use some transfer learning techniques presented by Oliver, and we just extract contour extraction, and then we use some standard image processing to extract all the contours. So this is a small b, and for each grayish areas of each contours, we just run a particular filter. But we still add some small fries for the contours, and we don't want them to for the functional principal component analysis. So to do that, we just do some cooking research using mainly correlation in time, and at the end we just end up with, for example, for this one, only one meaningful frequency ridge, which contain also almost all the other one inside. So the second step is the functional data analysis. So once we get the meaningful frequency ridges, we just smooth them, which means that we just try to remove all the short-term deviations and try to emphasize the specific patterns for each frequency ridge. Then we make like a big collection of all the smooth frequency ridges for specific code types, and we just do the decomposition of the variability for this code type. So you will see a bunch of these plots on the left. This is quite not really digest. So how can we read them and what can we expect from this kind of figures? So the interpretation is like the solid line in black, for example, on the upper left, is the mean of all the smooth curve, which are represented here with the different colors. And the dotted lines are just the variation around the mean. So the expectation for all these plots is to be able to identify, for example, the different parts of the curve with a solid line. And for example, for this S1, if we just have a look at the spectrogram from John Ford catalog, there are 3 parts, and we can more or less retrieve the 3 parts on the PCAs with the solid lines. We also want to answer the question, can we have a better understanding of the distribution of behavior within the code types? So, which means basically where does the variability lies for frequency ridges, and for S1 we can see that this is between the transition between the different parts of the code. For example, with this huge gaps between the dotted lines. So this is the next figures would be like results for the different call types. So for example, for S4, the solid line represents a small decrease of in frequency, and all the dotted lines and the variation can be explained because when we are doing the frequency ridge extraction, the frequency ridge extraction should just jump from one another harmonics because they are really close. And, the frequency ridge extractor is not perfect. But for example, for S19, we can retrieve like the general shape of the curve, which is more or less a small increase in frequency plateaus, and then an exponential increase in frequency. Not much variability, except that except when depending on the region which is tracked, you will have either like a small increase or just a flat plateau. For S16 and S17, it's more or less the same. We have flat lines, which is more or less the general shape of the curves. And for S16, we can have like at the end, we can have some variability at the end of the ridge, which depends on whether or not we have like the tail of the ridges at the end. For S36, this is like a good example of why we need like why we don't want to have like small fries in our ridge extraction process. Is because, for example, if we have like different lengths for our ridges, we can guess the variability distribution. And for example, if you see like the Sion line, so you see like a huge increase in frequency at the beginning, and the principal component analysis one just reflects this huge gap. So we don't know more about the distribution of variability for this S36. And for S44, we were able to retrieve the general shape of the high frequency component of the code. So this is more or less a call for all the expert annotators, because when you are doing research, you are trying to understand if this is something which would be useful for you, annotators to use like just ridge and to be able to compare the different ridge with the catalog of the different annotations. And it's an open question. what do you annotators do to annotate and to discriminate between pods or even code types? And just more or less jump with or join Oliver presentation. It's like, how do we do better together to have like annotation standard or shared catalog or even standardized practices of annotation between the different teams. So to conclude, these are still preliminary results to get distribution of specific code types based on frequency regions. Future direction would be like 2D approaches or even improving the ridge detector. There are like several caveats for these methods, because like there's some reason your way code types are really hard to study, and we've seen like some different example with our presentation or other presentation we had before. But there are like a lot of applications for having the distribution of variability for each code type, because we can obtain time-based distribution and we can synthesize new codes, but also classify them. We can also look for different structures between codes and between pods. This can maybe be an helper for annotations, and this can also be used for real-time analysis if you don't want to send too many information. And this is it. Thanks for all the partners and all the